Hello everybody, my name is Eric, and today I'll be going over how to create a function in Julia, and then later on how to use a function to do some Bayesian analysis using a binomial model. So the basic outline I just stated, cover how to use a function in Julia, go over the basics of Bayesian statistics, and use a function in Julia to deal with the binomial model. So here's some basic functions in Julia. So the top left one, we have a function called f where we take x, y, and z, and then we do some we have some math done to the functions in the body, x plus y times z, where we give x 5, y 3, z 4 equals 17. This is functions in Julia are pretty basic. If you've ever done any type of programming before, this shouldn't be anything new to you. If not, then hopefully this is helpful. So the bottom left one, I named this function 2, it takes 2 inputs, and with this function we have different types of math separated by commas. So in Julia you can do this to get more than one output. So I did a plus b, a times b, a plus b minus a times b, gives me 3 outputs, where I gave a is 9, b is 6. And then the one on the right basically just tells, kind of explains how the return function works in Julia. So I named this function g, give it x and y, and when the return function, or when the return word is read in Julia, the function stops. So in this case, the 2 times x plus 5 is what's going to be returned, and the rest will be ignored. If there was no return in front of that, then the x times y would be returned, and if there was no return in front of that, then all three would be returned. And so for this one we have x is 2, y is 4, gives us 9, which is that first formula. So using for and if statements, again, this is pretty similar to any other language, but this function finds us the hypotenuse of a triangle. So we give x and y for the sides, and then if the first if statement is satisfied, then it returns that formula you see there, x times the square root. And then if it's not met, it goes to the next if statement, and then if that's not met, it goes to the last one and returns y times the square root of 1 plus r times r. And if none of those are met, then it will return an error. But here I've covered all the bases, so the function will work. And as you see there, I've plugged in 3 for x, 4 for y, and got 5. So this indeed does work. And you will see how we use if in the return function when we do the Bayesian statistics concerning the binomial model. So a little intro to Bayesian statistics. So most of us are familiar with a frequentist perspective on data analysis, where we have data and then we just find a mean and a standard deviation, a single number, single value, and we're supposed to take that from the data. But in this case, we have parameters that are considered random. So we can create distributions around these random variables to give more of a meaningful analysis to the data. Instead of giving a mean of 120, we give a distribution around 120 to kind of give more flexibility and kind of show how far off the mean could really be from the average, which in this case was 120. So for our analysis, for the analysis in this video, we'll use a beta prior on binomial data, which gives us a beta posterior. So let's see what the math looks like. So here's the basic math for this one. So we have binomial data, as you see at the top, and then the prior distribution is beta, AB. And then there's Bayes' theorem right there, so we take the likelihood times the prior. And so the posterior is proportional to the likelihood times the prior, and then we end up getting a posterior distribution of beta y plus a and n minus y plus b. And here is the implementation of Julia. So I ran a binomial with n20 and the p of 0.3. So I ended up getting 5 successes out of the 20, which is the p hat of 0.25. So I use this find beta function to find the prior for this model. So I give it a mode and a percentile, and then I give it a vector of b's, and then it solves a little 2x2 system for a. And then I found the beta quantile for all the a's and b's, all the combinations of a's and b's, and found the max that is less than the percentile I want. Which in this case I think I gave it 0.25, and then it returns those values, and that will be our prior for this data. So yes, I wanted the mode to be 0.1 and the percentile to be 0.25, meaning that the center of the distribution was 0.1 and then the 95th percentile was 0.25. And that gave us a beta of 3.44 and 23. So this is going to be the prior, the A, and the B. So for the posterior, we have, for posterior, first parameter, we have y plus A, and then the second one is n minus y plus b, as you saw on the previous slide. So we simply just add 5 to A, which gives us 8.44, and then we add 15 to B, which gives us 38. So now we have a posterior beta, 8.44 and 38, and then if we were going to collect more data in the future, we could set this as the prior and then update it accordingly based on our data. So that's the gist of creating a function Julia and using a function of Julia to tackle some Bayesian methods. So in conclusion, we're going to use the same methodology to tackle the Bayesian approach to a normal model, which will be in our next video, where we have a normal prior on mu and a gamma prior on tau. And in this video we will use a Gibbs sampler because, unlike in this case, we cannot find our posterior enclosed form, so we have to estimate it using the conditional distributions. Thank you.